Okay, so today I want to talk about multiplicities. So the next couple of lectures will be to fix some properties of singularities. And today's lecture I want to focus on multiplicities. So let me first recall what the goal is. Okay, so I want to prove this Minkowski-Meining's theorem. So suppose that X inside X degree 4 inside 4 is a smooth quartic. And suppose I give you a birational map from X to some other, maybe another quartic, or maybe it's a projective space, or maybe it's any Mori fiber space, in fact. And I take a suitable embedding of the Mori fiber space in some projective space. So this is a birational map. And I can assume it's defined by a linear system inside some multiple of the anti-canonical class, which in the case of a quartic in P4 by junction, this is the same of the hyperplane class. Okay, so R in degree R, sorry, R times that. So R, you think about this as being the degree of the equations of phi. So phi is defined by a number of homogeneous form of degree R from the projective space restricted to X. And remember that we also have another number, which is 4, which is the degree of X. Okay. So, and then we prove this Noether-Fang inequality, which says that if I look at the pair 1 over X, 1 over RD, where D inside H is a general member, so some general divisor in the linear system defining the map, then this one is not canonical. Okay. In this case, the Picard number is 1, so there is no A. The only thing we need to look at is this pair. And if phi, so partial map is not an isomorphism. Okay, so I want to prove a contradiction. So in fact, I also have something more because there's some freedom. I can also look at the following pair, which is D intersect D prime. So this D prime, okay, let me maybe change. So what is it? D and D prime now are two general elements in the linear system. So because the variety is not smooth, every rational map defined on a smooth, in fact, on a normal variety, will be defined in codimension 1. Will be a morphism in codimension 1. So the indeterminacies of the map are in codimension 2. This is the same thing as saying that H as a linear system is going to have a base locus, but this base locus is in codimension 2 or higher. So it's a movable linear system. So what they say that this one is a complete intersection scheme of codimension 2. Because H is a movable linear system. Okay. So the idea is that here I have two types of informations. I have something about the degrees. I have the degree of the map, the degree of the upper surface we are looking at. But then I also have something about the singularities. And I didn't write the assertion that this is also not canonical. Something about the singularities. When we were on surfaces, for instance, when we looked at the Segre mining theorem on cubic surfaces, we were able to relate this information as information in terms of multiplicities. And once you do that, sorry, is there a question?
Yes, sorry.
Yes.
don't understand what does it mean that X 1 over R D intersection D prime is not canonical. So you want to say that?
Yeah, so I will, let's maybe not worry too much about this. So I will define, in fact, on Thursday, what this means precisely.
Okay.
So maybe what I want to say, so when you define singularity of pairs, there are kind of, in much of the literature, you work with pairs where there is a variety and some Q divisor. But in fact, you don't really need that to work with divisors. You can work with subschemes. And in the point of view, this proof is going to be actually very natural to do that. Because at the end of the day, really the pair that we look at, in fact, is the following one. So we is a base locus, is a base scheme of H, and this is not canonical. Okay, so this will be really the pair. And the other two pairs, they are different pairs, but in terms of singularities, they kind of have the same singularities. And this is just a consequence of the fact that if you have a valuation and you apply it to an ideal, it's the same as applying a valuation of a general element in the ideal, a general linear combination of the generators of the ideal. So we'll come back to this next time. So let's not worry too much about that. But yeah, this is actually a good point. So we're going to use pairs in this more general sense, which is natural in this context. Anyway, so we want to relate the two. We want to relate the two information. So what is the idea? Is that we want to translate the condition on the pair being not canonical into a condition of multiplicities. Then we want to apply Bézou's theorems. Okay, so this is a strategy of the proof. I have two types of information, degrees, and this will control how singular things can be. But in order to control that, I need to use Bézou, and Bézou can be expressed in terms of multiplicities. But then I have some information about singularities of pairs, and I'm going to have to link the two things together. And it's very important that we look at not just divisors like here, but we look actually at schemes, complete intersection schemes in this case. It's enough. So, but with that in mind, you can also already see that the notion of multiplicity is going to be a little more delicate, more general. We need a more general notion of multiplicity than just saying the multiplicity of a general element in the ideal. So if you have a Cartesian divisor on a smooth variety, multiplicity is just the multiplicity at a point of the local equation. So it's the lowest degree in a Taylor expansion of the equation, if you like. But we're going to have to work with a more general notion of multiplicities. So in this lecture, I want to focus on that. Okay, so let's talk about multiplicities. So there are several approaches to multiplicity. So here we follow Fulton's approach. Okay, so there are more classical approaches, and I'm going to refer to that in a moment. At least one of them, maybe the most classical one. In the end, they're kind of equivalent, but not really. So that's why you have to be a little careful. So first, let's start with a local setting. So suppose I start with Rm, some Noetherian local ring of dimension So here, really, what I'm thinking about is a case when R is a local ring or some varieties, where X is a variety, or maybe a pure dimensional scheme of any type. Okay. And then I suppose that A inside R is some M prime radio, which meaning it only vanishes at the origin, at the close point. So then you can define a Sine multiplicity as follows. Define, it's denoted by E of A. So this is a Sine multiplicity of the ideal in R. And this is the limit when M goes to infinity of what? The length of R modulo A to the AM as a R module divided by M to the N, and then I divided the denominator by N factorial. I put it in the numerator, but it's, I think people often write it as a denominator and denominator. So this kind of a renormalization. So what is this? This is a normalized by N factorial leading coefficient in the Hilbert polynomial. Okay. So equivalently, you can also see, suppose that is a local ring of a variety. So let me just call now spec the X, the spec of R. And then I'm going to look at the blow up. You take the blow up of the ideal A, X to X. And instead here, there is a Cartier divisor A, which is given by, so that A times or X tilde, the pullback of A is equal to X tilde minus A. So it's a exception divisor of the blow up. Okay. And then if you have this, then there is an interpretation of this number as an intersection number, which is -1 to the A minus 1 times A to the N. Okay. So let me give a name maybe to the Hilbert polynomial. So you got polynomial P of A, yeah. So the equality between the two follows by comparing the Hilbert polynomial PA to the Hilbert polynomial can we call it P capital A of A with respect to the of A of minus A, which is the same thing as of X tilde of 1 respect to A. So the two polynomials are different because they have different degrees, but one can be, you can show that one is asymptotically the difference of the other, and therefore they have the same normalized leading coefficient. So the point that this is a normalized leading coefficient of this P capital A. Okay. Let me maybe give you some examples. This, if you're not familiar with this multiplicity. So let me take in this example, I'm going to take R to be a polynomial ring or if you like, it could be the localization of the maximum ideal. You can localize the maximum ideal if you like. Okay, so the first example is a concrete example. Just take X to be a diagonal ideal, so is x1 to the d1 times xn to the dn. So x1 to the d1, xn to the dn are the generators of the ideal. So this cut out a primary ideal. In this case, the Sine multiplicity, because this is generated by a regular sequence, that's actually turned to be equal to the length of R mod A. So now you look at the length of R mod A is the same as the dimension of R mod A as in this case, as a K vector space. So as a K vector space, R is generated by all the monomials in the Xi's. And now I'm gonna set to 0 the x1 to the d1 and x all the way to xn to the dn. So this is gonna kill most of the monomials. You're just gonna have a kind of a box of monomials and if you just count them, you see that this is just a product of the di. In fact, this is a special case of the next formula that we're going to use later. So suppose A inside a polynomial ring is a monomial ideal. Which means IE is generated by monomials. Okay, so some notation. I'm going to use x to the u to express x1 to the un as a vector notation for monomials, xn to the un. And every time I fix an element, a monomial in A, I associate, to that I associate the point u, u1 all the way to un inside as z to the n, and all the entries are non-negative, of course, so z greater than 0 to the n. Using that, we can define the Newton polyhedron of A that is denoted by PA. So this is a convex hull of the set of u's such that x to the u is inside A. So this is a subset of z to the n. I actually regard this as a subset inside R to the n greater than 0. So the convex hull is computed inside there. So let me just give you maybe some concrete example. Just for an example. Suppose that A is, say, x to the 4, x cubed y, xy squared, and y cubed. So in this case, the dimension is 2, so we are inside R2. Okay, so let's mark 1, 2, 3, 4. So x4 gave me this point. Then the next one is going to be x3, y, which is this point here. 1, 2, 3. The next one is going to be xy squared, so it's down here. And the last one is going to be y cubed. So now, and then of course, these are just the generators of the deal. There are more elements here that I'm not marking down. But in fact, to write the Newton polygon, all I need is really generators. And now what I see is the convex hull, because I can multiply everything by R, every element every generator by R. So this gives a translation of the quadrant. And then I compute the convex hull of that. And so you see that the convex hull is going to look something like that. Okay. So everything on P A is all the region on the above this yellow line, the yellow curve that I draw. Okay. So in particular, the generator x cubed y was not really relevant information to compute the Newton polygon. So that's just to say that Newton polygon can be the same for different ideals. In fact, well, no, you don't see this in this example, but maybe there is an ideal where not all the points. Yeah, for instance, if I take B, oops, if I take B to be the ideal x to the fourth, xy squared, and y cubed, in this case, they would have the same Newton polygon, even though the generators of the second ideal don't include the white point left there. So the Newton polygon will be the same. But you see, when I look at all the monomials of the second ideal, if I mark them all down, I'm missing the white one. And so, okay, so the Newton polygon really it doesn't see really all the points. It doesn't characterize the ideal itself, and it maybe characterize the integral closure of the ideal. Okay, so this is what a Newton polygon is. So what you want to focus here is this region. You want to focus on this region here. This is Rn greater than 0 minus the Newton polygon. Okay. So, let's estimate the length of R of A to the M. When I estimate this length, so what is this? This is the cardinality of the set U inside Z to the N greater than 0, such that X to the U is not inside A. Okay. So what I'm gonna do is I'm gonna count. So let me maybe, I'm gonna count how many points are not in the ideal. But what I notice is that all the points here are certainly not in the ideal. Or maybe use a different color. All the green, no, this is too close by. All the, why don't, sorry. All the red points here are certainly not in the ideal.
Tommaso, sorry.
Yes.
You mean the length of R modulo A, not modulo A to the M.
Well, because I'm gonna do, yeah, so let's take M equal to 1, but let me write M. Let me write the M there. So in the picture is for M equal to 1, but I can do the same picture for every power of A, because at the end of the day, I want to take a limit.
Mm-hmm.
Yeah, so let me do this with, so all the red points there, and this one is a red point here now, they will be given monomials that are not in A for sure. And I don't know about this one. Maybe there are more monomials. Depends on whether the A contains that point or not. Would have the same Newton polygon or polyhedron. So what I see is that there is certainly a greater or equal here the size of all the lattice points which do not belong to the Newton polygon. There may be more, but at least that. And I'm doing this with A to the N. There's an M here, sorry. Okay. So, but now by just looking at this picture here, every time I have a point, I can build a little cube over it for every point. So I can cover the region by these little cubes. And this, there's also one here. So I cover the whole region. So what I see from there is that this is at least equal to the dimension, to the volume of this region, Rn greater than 0 minus the Newton polygon. Okay. And now here I'm using the fact that P of A to the M, this is not how to see that this is just M times P of A. So it's just a rescaling of the Newton polygon. So this will be equal to M to the N times the volume of R. And there is just for this guy. Okay. So what I see here is that so I have two inequalities, but in fact, equality holds asymptotically. So what I want to say is that if I now divide by m to the n, and I take a limit, and then I multiply by n factorial, what I see is that we get the Sine multiplicity of A is going to be greater or equal than n factorial times the volume of this region. And I say that in fact we have equality here. So let me just write equality. Okay, so let me maybe just say a word about why we have equality. What you see here, there are 2 points where we can get a strict inequality in the proof, right? So the first inequality is this one. This corresponds to the fact that I don't know if I need to also get this point. Maybe this point is not in there, and that will correspond to an additional square here. And the second point of the inequality is that even if I don't need to worry about this additional point there, I still have a kind of an error because I always still coming on top of the region. But if you take a powers, that corresponds to looking at P to the A and just taking a rational lattice where I start looking at 1 over mz to the n. So I'm adding more and more points around, and therefore the error gets smaller and smaller and smaller. And these points eventually will be there asymptotically. So I get more and more points along the edges. So if you just do this carefully, you see that this error, it grows lower than m to the n. And therefore at the limit it will go to 0. So this gives a formula for the Sine multiplicity of a normal ideal. And we're going to use this later. Any questions on this? Any question about this one? Sorry, maybe I mixed two steps at the same time. I wanted to get to this formula at the same time. The picture was just for P to the A, but yeah. So we apply this picture for powers of an ideal, which is you can see 2 ways. You either rescaling the Newton polygon, or you're keeping that fixed, and you are just dividing the lattice by taking fractions. Okay. So this was just an example, and this was our definition of a multiplicity of an n primary ideal in a local ring. So think about the local ring of a variety. Now with that definition, now we can define multiplicity of a variety of a scheme. Okay. What is the multiplicity of a variety X at a point? Well, I'm going to denote it. So this notation is, not many people write multiplicity with an E, but I'm going to do it following Fulton. So this by definition is just simply the Sine multiplicity of the maximal ideal of the point, where MP is inside of XP is the maximal ideal of the local ring. So let me maybe give you the example here. Suppose that X is inside maybe some affine space, n+1, some smooth hypersurface. Sorry, not smooth, some hypersurface. Maybe say locally X is defined by some equation h equal to 0. Then the multiplicity, and I say take P to be the origin inside an plus 1 will be the origin. Then the multiplicity of X at P is nothing else than the usual multiplicity at the origin of H. So it's a leading term, it's the degree of the leading term in the polynomial at 0. So the smaller degree of a monomial appearing in H. So it is what we're used to. In fact, more generally, if X is a Cohen-Macaulay variety, then you can prove that the multiplicity at X at P is the same thing as an intersection number at P of what? Of X with, is that a question? No. Maybe call it lambda, notation, inside inside some projective space. Inside there. So where lambda inside a capital N is a general linear subspace through P of complementary dimension. So this is a classical definition. This is what people would think about what a multiplicity is. So you have some varieties X, you pick a point P, locally you can always embed it inside some fine space. And then what you do is you're going to take a general lambda which intersect X in a finite set containing a point P. And then when you cut it down, you get a zero-dimensional scheme. You just compute the length of that scheme. So that's but this is not true in general. So this requires this Cohen-Macaulay assumption, for instance. So more generally, let me give a definition that we're actually going to need. What is a definition? What is a multiplicity of a variety or to the pure dimensional scheme X along a closed-up scheme Z inside X at an irreducible component T of Z. So it's a bit of a mouthful, but anyway. So this is denoted by the following multiplicity X along Z at this irreducible component. And that by definition is just the Sine multiplicity. You take the ideal of Z and then you just look in the local ring at T. So this equivalent is, you can be interpreted as the coefficient of the class of T inside the Segre class of the tangent cone, or the normal cone of X at Z. Okay, so we use, this is notice that if Z is already irreducible and reduced, so X is equal to T, then we write simply Et of X. Yeah. So the previous definition about the multiplicity at a point is just a special case of this. So we use the following property. Semi-continuity, given T an irreducible set, subvariety inside a variety of codimensional scheme X, we have that the multiplicity at P of X is always going to be at least a multiplicity of T at X for every T, for every P inside T. And equality holds for general P inside T, which means that there exists an open set T0 inside T, some open non-empty set, such that EP of X is equal to ET of X for every P inside T naught. Okay, so now that we have the definition in place, now we're ready to state some properties. So the first property I want to discuss here, first of all, is any questions about these definitions? So the first property I want to discuss is a Bezout type inequalities. So Bezout gives you a way of computing the degree of an intersection of some varieties, or maybe hyperplanes in a projective space in terms of degree of these equations, or the hyperplanes of the varieties. So there are two situations that we're going to run into that we want to use. So we're going to use the following two properties. Suppose I have Z to be the intersection XR inside Pn. So this is a proper intersection. Is a proper intersection of a subvariety V inside the projective space and R hypersurfaces HI in the projective space. Okay, so you suppose you start with some variety in the projective space, and then you start cutting down with hypersurfaces. So by proper intersection, in particular, this means that the dimension of Z is expected one, so it will be the dimension of V minus R. Then for every irreducible component, T of Z, we have that the multiplicity of V along Z as this component will be less or equal than the degree of V times the degree of the equations HI. Maybe, okay, write it this way. Okay. Back to this. Okay, so, well, what you do is that you take the restriction of the hi to v, and then you write this multiplicity. You can write this in multiplicity because this is cut down by a regular sequence. Then you write this as an intersection number. An intersection is done inside v. So this is an intersection number t of this intersection devices. Well, but this one certainly is bounded by the intersection product of these devices inside V. And now you can prove that, you can show that this is the same thing as intersecting H1. Let me maybe write. You will do this is the same thing as intersecting H1 times HR with the class of V inside the projective space. So then you use Bezout at this point. Okay, so this is the first one. So, I mean, this is a thing that you expect, right? You expect the multiplicity of right as a subscheme Z should be bounded by the degree of the equation cutting, the degree of the variety times the degree of the equation cutting the subscheme of the variety. The second one actually is simpler. Sorry. Suppose I give you now two varieties, V and W inside a projective space, two varieties of complementary dimension. Intersecting properly. Which means that when I look at the intersection, this is the dimension 0. Then what you see is that if I look at the intersection and I take the sum of all points of intersection for the multiplicity of the first variety, they will be bounded above by the intersection product of the two subvarieties in the Chow ring, which is just equal by Bezout the degree of V times the degree of W. So again, proof. So we're going to use Bezout for the second inequality. And the fact that when I compute the intersection product, I just look at, I need to compute certain intersection numbers or the point of intersection. But this intersection number are bounded below by the product of the multiplicities. Okay, so we have this bound. And then of course, just use the fact that this quantity is greater than 1. So I can neglect it, and I certainly get this formula. Okay, so these are, of course, this is nothing new really here. It's mostly just to say what kind of bounds from Bezout we're going to use in the proof. We're going to use these two forms of Bezout. So something you said new is the following properties. So now this is a result of Dublikov. Sorry, Dublikov's multiplicity bounds. This is bound. So let me now consider the following setting. So suppose that X inside some projective space is a smooth hypersurface. Of degree D. So, and I want to bound the multiplicity of cycles in X. So I'm gonna state it in the two cases we're gonna use. The first case is an easy case, and then there is a general case, and the second case will be the first interesting case of the general case. If you understand the proof of the second case and you have a sense of how the proof goes in general. But let me start with the easy case first. So this is the easy divisor case. Okay, so it says the following. For every divisor in X which belongs to a scalar by an equation of degree m, so it's an element in a linear system or Xn, we have that the multiplicity of D along any curve is bounded by m. And this is true for every irreducible curve C inside X. So it's not true that the multiplicity of D at any point will be bounded by m. So let me make a remark. Okay, if that's not true, for instance, take m equals to 1 and take D to be the intersection of the embedded tangent space of X with X. Then the multiplicity at P of D, use this notation because this is as a divisor on a smooth variety. Well, that's at least 2, right? I mean, I have an hypersurface. I look at the tangent space at a point P. And when I intersect, I get something which is singular at this point P. Okay, so you don't have a bound at every point. The statement here is that you have a bound along curves or higher dimensional cycles, subvarieties. Any questions about the statement?
Oh, sorry.
Yes.
Maybe I got lost. So the assumption is that X is smooth.
Yes.
Okay. Okay.
Yeah, X is a smooth hypersurface of degree D. We're going to use. You notice that D does not appear in the statement though, but it will appear in the proof. But yeah, X definitely is smooth. If it's single, of course, there is no way of controlling that. So let's prove this, and then we see what we need.
This is Zach's theorem on tangencies, right?
Excuse me?
This is Zach's theorem on tangencies. No?
Oh, well, I learned this from Publikov. So Publikov had a more general statement about, I would be, yeah, I don't know. I don't know if this is already, it's quite possible. I mean, definitely is kind of the proof, in fact, I can imagine is something that could be done with Zach. So yeah, if I need to look it up. I need to look it up. I don't know if it's already, I never really worried about that. But it is possible that maybe this is already in some more classical. Anyway, so let me continue. Okay, so first of all, let me assume that C is a curve inside the divisor, the support of the divisor. Otherwise, the statement is trivial. And the degree of X is at least 2. Otherwise, that's also a simple statement. So what I'm going to do is that I'm going to look at projection. So for every point P in the projective space minus X, I'm going to consider a linear projection. So I have a projective space Pn, and I'm going to take a linear projection by P to some hyperplane, if you think about, or just some projective space of one less dimension. So this is a linear projection from the point P. And then instead X, I also can project X also to HP. And because I pick the point of projection away from X, the induced map here is actually more fitting, FP. And so this is a finite map. Cannot contain any positive dimensional fiber, because all the fibers are P1s that goes to the point P, but P is not in X, so there's no fibers. So this is just fine. Finite map of degree D. Okay. So now, what is a ramification? So I'm going to take equation of X is defined by some equation, some 4 in n+1 variable equal to 0. So the degree of f is equal to d. And in these coordinates, P, we're going to have some coordinates, A0, all the way to AN. So an ramification divisor, which I denoted by Kx over HP, well, it's going to be cut out on X by the sum of the partial derivatives with coefficient AI, partial f with respect to xi, plus 1, 0 to infinity, equal to 0. So this defines, so this itself is a form of degree d minus 1. So what do we see from here? What we see is that this moves in a base point free linear system, because X is smooth. Okay, so we're going to use that. So I insist on not fixing coordinates depending on P, but rather fixed coordinates, and then I take a general P. I take a P, so that I see that there is a linear system.
Sorry, one question.
Yeah.
Could you quickly explain why the ramification divisor is given by this differentials?
Oh, this is just because well, now to explain this, let me actually change coordinates. So the P has coordinate 1, 0, 0, 0, 0. So the projection is simply dropping the first variable.
Okay.
Okay. So the fibers, I need to look at the sheaf of relative differentials. So I have all the differentials in all the variables, and then I differential in all the variables minus 1. So when I compute the sheaf of relative differentials, that's generated by dx0.
Okay.
And that's what is defining the ramification divisor. So sorry, this is on a projective space. Then I need to restrict to X, and this is where we pick up the partial derivatives of f.
Okay. And it's a pause series here, so it goes.
I mean, another way of saying this is that I'm looking at the place where the tangent space is. So a point is an ramification divisor if and only if the tangent space passes to the point P. the tangent space at a point on X is defined by that equation, by similar equations. And so when you plug the coordinates of P inside there, you want the equation of the tangent space to vanish there, and this is exactly this condition.
Okay, gotta think about that, but okay.
Yeah. Again, it's easier to see if you fix coordinates, so the point P is 1, 0, 0, 0, 0, and now you want the equation of the tangent space to be x0 equal to x, you know, 0 equal to 0. Anyway. So what do we do with that? So now we're gonna pick P general. Oops. So you're gonna fix C and pick P general. So let me draw a picture here. So this is X, and I'm projecting now from a point P. The point P is up on the top. I'm projecting now down to some space HP. This is a file map, and I have a curve C going through here. So what I'm going to do is that this map is FP. I'm looking at FP of C. So this would be a curve. The map from C to this image will be a birational map. So this curve is still going to have degree equal to the degree of C. Degree of C is some number. Now what I'm going to do is that I have FP of C, and then I take the inverse image of this. So if you like, you take a cone over this projection over the curve of the image of C. When you do that, you're going to get a residual curve of intersection. So this will be equal to C union R. So this is a residual curve of intersection. So when I intersect with the think about you doing this in a projective space, you're taking a cone over the image of C, and this is going to be some surface, and then intersect with X is going to, well, of course, C is going to be in there, but then it's going to be the residual intersection. And what I see is that this is a curve of degree equal to what? Well, the X has degree D, so the image of C has degree of C. So when I take the inverse image of that and intersect with X, I get something degree D times the degree of C. But then there is one component that I'm removing. So what I'm left with is D minus 1 times the degree of C. And what I see is that for general projection, C, so maybe I want to say that R meet, let me just write it this way. Intersection, so they meet, let me maybe one, sorry. C intersect R contains the intersection of C with the ramification locus, which is the support of this divisor. Okay. But for a general P, because the ramification divisor moves in a base point free linear system, I can assume that it's going to cut C in a reduced set. And by just comparing equations, so I see that this thing here is a reduced set. It's a set of how many points, where degree of C times the degree of the form cut in the ramification, which is D minus 1 times the degree of C by distinct points. Okay. But now remember that we have a divisor D also. So the divisor D, I'm assuming that it goes through C with a certain multiplicity. So this is a divisor D. So it's going through the curve C. The curve C was this one. Okay. So now I'm going to compute. I'm going to compute the intersection of D with the residual curve. So I can assume that the residual curve is not containing D. By taking a general projection, I can always assume that this is not containing D, so it intersects properly. And well, if I compute the intersection, I know the degree of D. So D is a cycle of degree D minus 1 times the degree of C. And then I'm cutting with something, but with a form of degree M. That was my assumption on D. So it was cut by a form of degree M. So there's the degree of intersection of D with R. But now what I'm going to use one of the Lezione inequalities. It tells me that this intersection product is at least the sum of the multiplicity of one of the two varieties in the intersection. And I'm looking at D. At which points? All the points of intersection. Okay, well, that's certainly because I'm going to write the same thing, but now I receive my intersection on C intersect R. There might be other points of intersection, but I have no control of those points of intersection. But now certainly going to contain intersection along C. Okay, but now these are the points we understand, because I know that the multiplicity of D at C is bounded above by the multiplicity at each individual point in C. So this will be greater or equal than the multiplicity of D at the curve C times how many points are there. And this we compute that contains at least D minus 1 times the degree of C points. Okay, so this one is the number of points. Is a estimate, is a lower estimate of the number of points. Okay, but now if I just compare what I wrote, so this implies that EC of D is less or equal than N. Okay. Which is what we wanted to prove. So what is interesting here again is that the degree of X does not come in this bound. This bound is independent of the degree of X. Okay, any other questions on this? Okay, so let me now look at what we have and what we need. So this is enough. To prove the Iskowski-Manning theorem. In fact, it simplifies as a regional proof of Iskowski-Manning. Iskowski-Manning, they had to study some low dimension, some low degree curves and use a little bit more geometry of these curves on quartic threefolds to conclude. But in fact, this will take care of that part faster. However, in order to prove the high dimensional generalization of Minkowski-Mining theorem, we need the following. Version. For codimension to subscheme. It's really about cycles, but let me just state it for subschemes. So this is a two-dimensional, the codimension 2 case. So as before, X inside some projective space is a smooth hypersurface of degree D. And now I'm going to consider Z inside X are pure dimensional closed subscheme of codimension 2. We're going to assume that Z is numerical equivalent or rational equivalent, if you like. So the class of Z is numerically equivalent to M times C1 of O X of 1 square. Okay? So it's rational equivalent to M times the restriction of intersection with two upper plane classes. Then, if I look at the multiplicity of Z at any surface this time, is less or equal than M. And this is for every surface S inside X. So again, the key point here is that D does not appear in this bound. So this bound is independent of D. You notice that as we increase in the codimension, we are also increasing the dimension of the cycles on which we are estimating the multiplicity. So I will not be able to say anything about the multiplicity of Z at points, of course, but also along curves. So in principle, multiplicity along curves, they might be bigger, may actually be more comparable to the degree of X as well. But as soon as they go to surfaces of high dimension, then I can bound the multiplicity uniformly, independently of D. So we're going to use this one when you're going to deal with the high dimensional theorem. There is a general statement where you look at cycle of codimension K and then multiplicity along subvarieties of dimensional K. But let me not worry about that. So the proof, if you see how the proof goes for this case, then you can imagine what you need to do for the general case.
Sorry, I'm a little bit lost.
Yes.
Is M a proportional factor between the numerical class of Z and the square of C1?
Yes.
Okay.
Yeah.
No. Okay.
Yeah, exactly. So like before, M was just a degree of a form cutting out the divisor. So it was this is just a, the point is that at the end of the day, we're going to just compute some intersection numbers. And all I care is what kind of intersection comes from Z, the contribution of Z to the intersection number. Okay, so let's prove this. again, let me assume that S is a surface in the support of Z, and if the degree is at least 2, otherwise it makes trivial. And again, as before, I pick a point in the projective space as a general point, and then I look at the projection Fp from X to HP, which is some projective space, one less dimension. So this is a finite degree d minus 1, degree d. Okay. So now I want to repeat the argument I did before. So let's go through that. So I'm going to draw a picture first. So this is X. And then projecting this X to some plane, hyperplane, HP, by this map FP. So now I have a surface here. Yes. So when I project, I get a birational map to this image, which is FP of S, and the degree of the image is the same as the degree of S. And now I take the inverse image, so I look at FP inverse of FP of S. For general projection, at least the support, I can always write it, and a bit sloppy here, maybe, but anyway. There's a support as a union of two subvarieties, where one is original variety, a surface S, and the other one is a residual surface of intersection. So it will be some other surface R here. What you notice here, so first of all, what is the degree of R? Where the same argument as before is telling you this is d minus 1 times the degree of S. Another thing I want to notice here is that now S intersect R is as dimension 1. Okay, so it's some curve here. Intersection is a curve. So I want to cut down to points. So this I'm not quite there yet. Because if I now intersect with Z, so Z will be some other scheme, maybe write it. So Z will be some other scheme here which contains S, right? But Z and R do not intersect properly. Yet, okay? Because they have complementary dimension, but the intersection, it contains a curve, so it's not proper intersection. So I cannot make any estimate on the intersection numbers, on the multiplicities yet. So the idea is that I iterate the constructions. Now forget about S, because S was fully contained inside Z. And when I did this projection and computed the residual surface of intersection, I reduced the dimension of intersection with Z by 1. I went from dimension 2 to dimension 1. So if I do this one more time, then maybe I have a chance to get something which intersects properly. So, so we're going to repeat the process. So we're going to pick P prime inside Pn, another general point. And now I'm going to do the same thing, Fp prime inverse of Fp prime of what? Of R. And I write this as R union R prime. And now what is the degree of R prime? The degree of R prime, well, will be the same by the same argument, is d minus 1 times the degree of R. The degree of R we computed before is up there. So this is the same thing as d minus 1 squared times the degree of R, the degree of S. Okay, so I'm gonna let K be the ramification divisor for the first projection, and K prime in the ramification divisor of the second projection. These are two general elements in a base point-free linear system. Okay, so what I see is that if I intersect S with K and then intersect it with K prime, I get a zero-dimensional scheme. And it also is reduced. In fact, it consists of the degree of the equations is d minus 1, so two equations, so d minus 1 square times the degree of S distinct points. So you can see where I'm going, because now what we get is a matching between the degree of this residual surface of intersection R prime and the degree of the points cutting on S by the ramification divisors, with the number of points. Also, I see that S intersect K, the point of ramification, will lie inside the intersection with the first residual surface. And now what I do with starting from R, I have a similar property that this is contains at R intersect R prime. So when I put these two together, I see that this set, I know how many points, I understand the cardinality, is contained inside S intersect R prime, which is a finite set. And now, using the piece general, where we already argued that this means that the first residual surface of intersection intersects Z in dimension 1, so the intersection with Z with R is 1. And now, taking the second one general, one can ensure the intersection of Z with the next one goes down to 0. This actually requires some computation that I'm going to omit here. And again, this guy here contains S intersect R prime, which contains S intersect K prime. And now we are ready and then say that intersecting dimension 0, so finally I have two cycles that intersect properly, so I can compute their intersection. So I look at Z dot R prime. So let me actually give some a little bit more space. Z dot R prime. Well, I know what this is. So R prime is something of degree, this is minus 1 square times the degree of S. And Z is proportional to M times a linear class, sectional linear class. So I'm going to get M times this quantity. That's the intersection number. Now, using this inclusion of finite sets and the fact that I control the cardinality of the smallest one, so first of all, this certainly is at least a multiplicity at the point P of Z at all the points of intersection, at least at those that are contained in this set S intersect K prime. And then as before, this will be greater or equal than the multiplicity of Z along the surface S, because all these points belong to S. Z. Did I forget something? Oh, times the number of points, which is d minus 1 square times the degree of S. So this again implies that ES of Z is less or equal than M. Okay, that's the end of the proof. So this is the idea. Again, in order to ensure that the dimension goes down, one needs actually to compute some secant varieties and so things. But I'm gonna skip that part in the proof. But that's the strategy. And then you can imagine that there is a more general statement there. But those are the cases we're gonna need in the proof. We're gonna use in the proof. Any questions?
Tommaso?
Yes.
So in a sense, these are kind of Hurwitz arguments. So you use the ramification. Am I also in the general case?
Yeah, I don't see really the connection though. But maybe. I mean, yeah. I mean, the ramifications. Yeah, I guess. In a way, yes.
No, just to have an idea of the general framework.
Yeah, I mean, it's a bit different because the projection on the cycles is actually birational. Because you project to something which is bigger dimensional. So for general projection, you can ensure the map is birational. But the ramification from the ambient variety will tell you how many intersections with the residual components you have.
Okay.
Yeah, that's where the ramification comes in. Allow you to count these points.
Okay, thanks.
Yeah. Okay, other questions? I think we can finish a few minutes earlier today.
Sorry, it's me again. Do you have a reference? So this
Yes. I put a reference in the notes. So
okay. Okay.
if I remember correctly, so Publico has several papers on this on the birational rigidity problem. So I think this the first proposition, I think, is in a paper by Publico from '98. So this is a case where he's studied the general case, but assumes some the equations of the upper surface are generally moduli. Using that, you can control, you have more control over what kind of cycles you are containing to the upper surface. And then the last case, this one is more recent, maybe it was in 02, the paper appeared in 02.
Okay.
Okay.
The general case, I mean, you produce K general projections, something like this, no?
Correct. Every time you project from a point, but you pick K points. Every time you project, so you have a cycle, S becomes something of dimension K. And then Z is going to have codimension K, S is contained inside Z. So it's, at the first stage, it's fully contained inside Z. You do the first operation and you get a residual thing with intersection is in dimension K minus 1. You project again and the intersection goes dimension K minus 2, and you go do K times, and you get something at the end which intersects properly in a finite set. You keep track of all the degrees.
Section dimension at any steps before, so that you arrive at the exactly zero dimensional. Okay.
Exactly. So that's the goal in the construction. You iterate until you get something zero dimensional. The degree is going to be d minus 1 to the k times the degree of the cycle, S that you started from, the variety S. And then the same proof goes through again. One need to be proofs, the thing that I didn't prove today, that the fact that the dimension does go down at each step. That's required. Okay.
Tommaso, is there a version of this for complete intersections?
That's a very good question. Yeah. There is. It's not obvious that the proof works. Let me explain why. So here, let me go back to the original setting here, or even the easy case. So the proof works by comparing two numbers, which are the degree of the residual curve intersection with the number of distinct points that you have with the ramification divisor. So now, suppose you have X is a complete intersection, maybe defined by two equations, degree D1 and D2. So now you run into the problem that the degree of X is a product, but the degree of the ramification is given by the sum of. So at the end of the day, you're going to have, in the first place, you're going to look at something like D1 times D2 minus 1. But in the second case, I think you're going to look at something which is more like D1 plus D2 minus 1, maybe. I don't remember exactly. But somehow there is a discrepancy there in the computation of the degree of the ramification with the computation of the degree of. It's been many years since I actually look at that. But there is a. So this guy, Fumiaki Suzuki, give a version of this for complete intersection. Okay, again, it's not very fresh in my memory, but it's possible to do this. So at the end of the day, you get some similar statement. There are some conditions on the degrees, I think, if I remember well. But the proof was definitely more involved. It was not so simple.
Okay, thanks.
Yeah. Yeah. Other questions? Okay, so maybe they can first start.